Hello, everyone, and welcome to Lecture 24 of Computer Architecture. Today, we're going to start talking about a very important optimization in computer architecture, and that is pipelining. Review of what we did last time. Last time, we looked at the data path, and we focused on the control signals in the data path. And we saw how we have these control signals that control all the different structures in the data path. And we saw how these control signals are determined by a control unit that uses the opcode to do that. And we also have a special controller for the ALU that uses both the information it gets from the main control unit based on the opcode, but also the funct field, because for R-type instructions, the funct field also determines the operation that the ALU needs to do. We looked at jump instructions, and we saw how to extend the data path to support jump instructions, and that is by adding this logic over here that computes the jump address using PC relative addressing by multiplying the 26-bit address field in the jump instruction by 4, and then concatenating it with the top 4 bits of PC plus 4, and that's what's going on over here. And then after that, we looked at the truth tables for the main control unit and also the ALU control unit. So this is what we covered last time. Does anyone have any questions about this material before we move on to today's material? Okay, if there are no questions, then today we're going to talk. Oh, and then also last time I did speak a little bit about performance issues. We said that load instructions are the critical path in the pipeline. So the load instruction is what's going to determine the duration of my clock period. Talking about pipelining, and talk about pipelining, what I'd like to do is I'd like to give an analogy with doing the laundry. Okay, so laundry is something that many of us do, and there's different steps, multiple steps for doing the laundry. You put the laundry in the washing machine, and the washing machine washes the laundry. Then you put the laundry in the dryer, and the dryer dries the laundry. And then you need to fold the laundry, and then you need to pack the laundry in the closet. And let's assume that each of these steps takes 30 minutes to do. So when you come to do the laundry, you spend 30 minutes washing, 30 minutes drying, 30 minutes folding, and 30 minutes packing the clothes in the closet. So what is the total amount of time needed for one person to do their laundry? Right, 2 hours, exactly. Easy question. So the time for one person to do their laundry is 2 hours. Now the question is, if I have 4 roommates who are living together, right? So they're sharing the washing machine, the drying machine, the folding table, etc. They're sharing these resources. So if I have 4 roommates who would like to do the laundry, how long does it take for 4 roommates, for all 4 roommates to finish doing their laundry? Okay. Well, they don't each have their own washing machine and dryer, right? They have the same. They're living together, so they're sharing these resources. Okay. So it cannot possibly take 2 hours. However, someone answered 8 hours, and that is one possible answer. And the real answer is that it depends on the strategy that they follow for doing the laundry. Okay. So let's see different possible strategies. So one possible strategy to do the laundry for these 4 roommates to do the laundry is that the roommate A comes and they do their laundry, and that takes 2 hours. Okay, and then once roommate A is done, roommate B comes, they do their laundry, that takes 2 hours. And then when roommate B is done, the roommate C comes and they do their laundry, and that takes 2 hours. And then after that, roommate D comes and they do their laundry, and that takes 2 hours. Okay. So someone's saying that they can fold and pack at the same time. No, we're assuming that they can't fold and pack at the same time because the folding table is only enough for one person to use it, and you can't have multiple people using the closet at the same time because the closets, they're all using the same closet. Okay. So one way to do it is this way. right? So in this case, how long will it take for the 4 roommates to do the laundry? Right. This total time is gonna take 8 hours. Okay. But yeah, and this strategy over here is does not use pipelining. Okay. So this is kind of a naive strategy for roommates to do the laundry. Now 8 hours is a lot of time, right? And especially if you're the last roommate to go, you're probably not going to be happy about doing your laundry from midnight to 2 a.m. You probably want to be sleeping during that time. So it would be nicer if we had a faster way for the roommates to do their laundry. Now, each roommate is still going to have to spend 2 hours doing their laundry. That you can't get away from that. But it would be nicer if all together they could finish sooner. So, any ideas about what we can do to make them finish sooner?
Sir, the
Yes.
first one start with washing. When he proceed to drying, the next one comes and start washing, and this should take maybe 3 hours or 2 hours, 30 minutes.
Right, exactly. So one thing we could do, we'll notice here that so the washing machine, it's only being used, it's not being fully utilized, right? It's only being used during this 30 minutes, and then it's not used for an hour and a half. Then it's used during these 30 minutes. Then it's not used for an hour and a half. So for the second roommate B, they don't have to wait for roommate A to finish doing everything in order for them to start doing their laundry. As soon as roommate A is done with washing, roommate B can start washing, and then by the time roommate B finishes washing, roommate A is done drying, so roommate B can start drying, and that is exactly what pipelining is. So if you look at the diagram below, a more efficient way to do this is for roommate A. When roommate A is done washing, B will start washing while roommate A dries, and then when roommate A is done drying, B will start drying, and in the meantime, C will start washing. And then when roommate A starts packing, during this time, B is done drying, so B can start folding, and C can start drying, and D can start washing. And then at the end, they keep doing this until they are done. And you'll notice that this time, it takes much less time, right? It takes 30 minutes plus 30 minutes plus 30 minutes plus 30 minutes plus 30 plus 30 plus 30. So it's going to take 30 minutes for each roommate, and then the tail over here, the remaining stages, which is 30 minutes times 3. So here the total time that it takes with pipelining is 3.5 hours. And this way, all the roommates are done doing their laundry. The last roommate is done doing their laundry by 9:30, which is much better than 2 a.m. Okay, so this is exactly what pipelining is. Any questions? So pipelining is a very simple concept. We use it all the time. We use it, in this example on a daily basis, in daily kind of operations we do at home. So laundry is an example. It's also used in all kinds of factories. When you have these assembly lines and factories, they want to build things, and there's different steps in building a product. So they use pipelining all the time. And of course, we use it in computer architecture in order for us to improve the performance of our processors. So let's take a look at how we can use pipelining in computer architecture. Actually, before that, I'd like to kind of briefly comment on pipelining in general. So in general, if my pipeline stages are balanced, which means all the different stages in my pipeline take the same amount of time, which was the case in the laundry example, then if I have S stages to my task, and each stage takes the same amount of time, we will call that TS. And if I want to perform N tasks, then the time to perform these tasks without pipelining is N times S times TS, right? So N is the number of tasks times the number of stages per task times the amount of time per stage, okay? So the total time for without pipelining is going to be N times S times TS. The total time with pipelining is going to be N plus s minus 1 times ts. Where did I get n plus s minus 1? Well, if we go back to the diagram here, the amount of time that it took to perform these tasks is you count the first task for all you count the first stage for all the different tasks, okay, and then you count the remaining stages for the last task, and that's how you get the total amount of time. So this is where s minus 1 came from. You have the first stage for all n tasks, and then the remaining stages for the last task. That's s minus 1. Okay, so n plus s minus 1 times ts, this is the time with pipelining. And the speed up is going to be the old time over the new time. So it's n times s times ts over n plus s minus 1 times ts. And for very large n, if n becomes very large, then you can cancel out ts. And here s minus 1 becomes negligible. And so you cancel out n over n, and you're left with s. So for a very large n, pipelining a task to s stages gives you a speed up of s. So if you have thousands of roommates living together doing the laundry, then pipelining will help them finish the laundry 4 times faster. Okay? All right, so let's see how this applies to computer architecture. So in the MIPS pipeline, it turns out that we can take the data path that we built in the previous 2 lectures, and we can pipeline it in order for us to get better performance. How do we do that? Well, the MIPS data path can be divided into the following 5 stages for pipelining purposes. The first stage is the instruction fetch. Okay, so we can consider the part of the pipeline where we fetch the instruction as one stage. The second stage is the instruction decode and register read. We call this the ID stage. So instruction decode and register read, this is the part of the data path that takes the instruction that we fetched, reads the registers that we need, and also uses the controller to decode the instruction to figure out all the control signals. Okay, and there's also the sign extension if we have an offset. So this is the part of the data path. This is the second stage of the data path. The third stage is the EX stage, or the execute. This is where we execute the operation or calculate the address. And this is essentially the stage that uses the ALU. Okay, so the ALU is the third stage in our pipeline. The fourth stage in the pipeline is the memory stage. And this is where we use the data memory to either load or store a value. Okay, calculating the address will be done in the third stage if we have a load or store instruction. And the actual load or store will happen in the mem stage. And then finally, we have the write back stage, where if we computed a value and we need to write this value to a register, we do this in the fifth stage. So this stage corresponds to writing to the register file, as opposed to reading from the register file in the ID stage. Okay, so these are the 5 stages of a MIPS pipeline, and it turns out that in hardware, these stages are not really well balanced. So in our laundry example, we made a simplifying assumption that stages are balanced; they all take the same amount of time. But it turns out that in hardware, the stages are not actually balanced in this MIPS pipeline. So what we will do is we will assume that the ID and the write back stage, so these are the 2 stages that read and write from the register file, we'll assume that these take 100 picoseconds. And for the other stages, so the instruction fetch, the execute, and the memory, we'll assume that these take 200 picoseconds. Okay? So assuming we do this, so someone's asking, you mean after reading from memory, we increment the PC immediately? No, the PC is going to be incremented in the instruction fetch stage, not the memory stage. Okay, so the instruction fetch stage includes both reading from the instruction memory and incrementing the PC. Okay. Oh, so you mean reading from memory as in reading the instruction memory? Yes. So incrementing the PC is part of the instruction fetch stage. Okay. So then this is what we will assume. So now let's take a look at the performance that we can get from pipelining the data path. So today I'm going to talk about pipelining the data path at a high level and see what are the benefits of that and the challenges with doing that. And next time we will look at how do we actually apply this pipelining in the actual hardware. So how do we modify the actual data path to do pipelining. Okay, but now let's just take a look at this abstract. So without pipelining, if I wanted to execute 3 instructions, for example, let's say I had 3 instructions I wanted to execute without pipelining, it will look something like this. So we said that all the stages are 200 except the read and the register read and register write are 100. So we have 200 plus 100 plus 200 plus 200 plus 100. That's a total of 800 picoseconds for each instruction. And what I did in my previous data path is I assumed that the instruction is going to take an entire cycle. So what we do is we're going to execute one instruction, and when this instruction is done, we execute the next instruction, and when this instruction is done, we execute the third instruction. So each one is going to take 800 picoseconds. So what is the total amount of time needed for these 3 instructions? Right, 2,400 picoseconds, exactly. So for 3 instructions, we need 2,400 picoseconds or 2.4 nanoseconds. Okay, so what if I apply pipelining? What if I apply pipelining? Well, if I apply pipelining, one of the things I need to be careful is that all the stages are not the same duration. Okay, but when I apply pipelining, the way pipelining works is that all the stages need to have the same duration. So what's going to happen is that even though the register read and the register write stages, the ID and the write back stage both take 100 picoseconds, we're actually going to give them 200 picoseconds of time to do what they need to do. Okay, and the reason is that the other stages take 200 picoseconds. So with pipelining, things are going to look like this. We're going to have the first instruction does instruction fetch, instruction decode, execute. So this is the ALU, data access, and then write back to the register file. As soon as the first instruction is done with the instruction fetch, the second instruction can now do the instruction fetch. So as soon as I'm done fetching the first instruction, I can go on and fetch the next instruction while the first instruction is in the instruction decode stage. So while the first instruction is reading from the register. And on the third cycle, as soon as the first instruction is done decoding, so it can execute, it can use the ALU. During this time, the second instruction is now fetched, so now the second instruction can read from the register file, and the third instruction now can do the instruction fetch. Okay, and so on. So if we do this, now a single instruction is actually going to take more than 800 picoseconds, and the reason is that we had to stretch the decode and the write back stages to be 200 picoseconds like the others. So in this case, a single instruction takes 1,000 picoseconds. However, how long is 3 instructions going to take? Right, so 3 instructions are going to take 1,400 picoseconds. So we have 200 plus 200 plus 200. That's the first stage of each instruction, plus the remaining stages, which is 200 plus 200 plus 200 plus 200. So this is 1,400 picoseconds. Okay. So someone's asking which part is responsible for the difference time? Well, the reason we have a difference in the time is that not all the stages are the same duration. Okay, so because we wanted to pipeline this data path, since this instruction decode and this write back stage are 100 picoseconds, not 200, but we wanted to overlap them with instruction fetch, right? So what we had to do is we had to make them take 200 picoseconds, even though they don't need that much. Okay, because if we finish this register decode over here in 100 picoseconds, we can't start the ALU stage. Or actually, maybe let me look down here. So if you look down here, if here I have an instruction fetch. If I finish my instruction decode in 100 picoseconds, I cannot start my ALU stage because the previous instruction is still using the ALU. So we have to wait for the previous instruction to finish using the ALU before we can use it. So that's why even though the instruction decode needs 100 picoseconds, we need to give it 200 picoseconds because we won't be able to use the next stage anyways. Okay? Okay. So someone's asking if we can pipeline without making them take 200 picoseconds. So I'm not sure I understand your question. You're saying that you want each stage to take less than 200 picoseconds. I mean, that just has to do with optimizing the individual stages, right? If you want each stage to take less time, you have to optimize the individual stages. That doesn't really have to do with pipelining. Okay, now one thing you can do is you can have a deeper pipeline. So what you could do is, instead of dividing it into 5 stages, maybe you can divide it into 10 stages. Okay, and then do it over 2 cycles, over 2 stages. For example, this is these some things you can do, but don't worry too much about that. For now, let's just assume that we have a 5-stage pipeline. Okay. All right. So now we can see. So in general, so here this is for this specific example how much performance improvement we get. In general, if our stages are not balanced, and if we assume that we have n instructions, okay, then the time without pipelining is the number of instructions times 800 picoseconds. Okay, so that's n times 800. And the time with pipelining is going to be n plus 5 minus 1 times 200 picoseconds. Where did I get this from? Well, I'm going to have number of instructions. Okay, so I'm going to have the instruction fetch for all the instructions, and then plus the remaining stages, which are the remaining stages for the last instruction, which are 5 minus 1. So there's 4 stages remaining. Okay, so this is where I get n plus 5 minus 1, and then each stage is 200 picoseconds. Okay, so we have n plus 5 minus 1 times 200 picoseconds. Okay, so if we have a so the speed up is going to be the non-pipeline time over the pipeline time, so n times 800 over n plus 5 minus 1 times 200. So when n is very large, the 5 minus 1 here becomes negligible, so we just eliminate n and n from up and down, and we get 800 over 200, which is 4x. So when n is very large, pipelining our data, applying pipelining to our data path gives us a 4x speedup. Even though we have 5 stages, we just have a 4x speedup, but still 4x is a very good speed up that we get from an optimization like pipelining. Okay. Any questions? All right. Well, pipelining is great. It gives us a lot of good speed ups, makes our data path faster. But there's a catch. There's a problem, and this problem is hazards. So what are hazards? So a hazard is a situation that prevents an instruction from executing a pipeline stage in the next cycle. And the reason that we have hazards is because now all of a sudden what we're doing now all of a sudden is that we're overlapping the execution of these instructions. Okay, so rather than executing one instruction and then the next and then the next, we're starting to overlap the execution of these instructions. And since we have multiple instructions kind of executing at the same time, we can get into certain situations where an instruction cannot execute because of something that another instruction is doing. And let's take a look at the different types of hazards. So we have different types of hazards. The first hazard is a data hazard, and a data hazard occurs when an instruction cannot execute because it needs to wait for another instruction to complete its data write. So an instruction needs data from another instruction that is currently executing. So I can't begin the instruction that needs the data. Another type of hazard is structure hazard. And a structure hazard occurs when an instruction cannot execute because it needs some hardware resource. So it needs a hardware structure that another executing instruction is currently using. And again, this comes from the fact that we are overlapping the execution of these instructions. And then the third type of hazard is control hazards. And control hazards take place when we cannot decide what is the next instruction we would like to fetch, because what the next instruction to fetch depends on the outcome of an instruction that is still executing, that hasn't finished. Okay, so let's take a look at an example of these three kinds of hazards. So I'm going to start with data. So again, a data hazard occurs when an instruction needs to wait for another executing instruction to complete its data read or write. So let's take a look at an example. So let's say I have an add instruction over here. Okay, and this add instruction writes to the register S0, and it's followed by a subtract instruction, and the subtract instruction reads the value S0. Okay. So now let's take a look at what happens when we try to use a pipeline to execute these two instructions. So first I fetch the add instruction, right? And then I decode the add instruction. So I'm going to read T0 and T1 from the register file. And then I execute. So here I'm going to be adding T0 and T1. And while I decode, I'm going to do the instruction fetch for the subtract instruction. And then I'm gonna use the ALU to do the addition. And in the meantime, I want to come and do instruction decode for subtract. So I want to read S0 and T3 from the register file. But what's the problem here?
Sir, which S0 are we reading in the next instruction?
So exactly. So here, if I write an instruction add S0 T0 T1, and then I write another instruction sub T2 S0 T3, I expect that the second instruction sub, the subtract instruction, is going to use the S0 that the add instruction wrote, correct? That's what I would expect. However, the problem here is that when I pipelined, now I'm trying to read S0, the subtract instruction is going to try and read S0 from the decode, but the problem is that I haven't actually written S0 yet. Okay, so the add instruction still hasn't written S0 to the register file. It does it on the write back stage, but now subtract is trying to read S0 before it got written. And this is a problem, right? This is a problem. We can't have this. We can't have the subtract instruction read from the register file, read S0 from the register file, if the add instruction still hasn't written to the register file. Okay, so what can we do here? What can we possibly do to solve this problem? Extend? So what do you mean by extend? So what we can do is, rather than letting the subtract instruction execute, we're going to make it wait. Exactly, right? So we make it wait. So one solution is, and this is called stalling. Okay, so one solution is to stall the instruction until the data hazard is gone. And we think of this as inserting bubbles in our pipeline. So in other words, rather than doing instruction fetch for this, rather than kind of beginning the subtract instruction on the next cycle, over here, what we will do is we will stall until it becomes feasible for us to execute the subtract instruction without a data hazard. So this is one possible solution. Okay, so here if we wait for 3 cycles and then we start the subtract instruction. So here we will do instruction fetch for the subtract instruction when the write back is happening. And then we can do the instruction decode on the next cycle. And by this time, the write back is complete. So it's safe to read S0 from the register file because it was written to the register register file in the previous step. So someone's asking, can we add special hardware to loop back the value? Yes, we can. I'll talk about that next. Okay. Actually, not next. There's one more thing I'll talk about, and then I'll talk about that. But yes, that's a good observation, and we'll get to that. Okay, so this is one thing we can do. We can stall, okay, until we no longer have a data hazard, until the write now happens later in time after the read happens later in time after the write. And now the problem with stalling is that we have many cycles are wasted, right? So if we stall every time we have something like this, we waste many cycles, and this is very common. It's very common for an instruction to write a register and then the next instruction to read that register. This is something that happens a lot, and we'd rather not have to stall for 3 cycles every time we have this situation. Otherwise, it beats the whole purpose of pipelining. Okay? So there are some other optimizations that we can do to avoid having to stall this much. Okay? One thing we can do, so someone's asking, can we do other operations in between? Yes, we can, and I'll also take a look at that later. Okay, but one thing we can do is the following. We can do is we can allow for, since the write back stage only takes 100 picoseconds, and the reading from register file also only takes 100 picoseconds, what we can do, so remember before when we did the data path without pipelining, what we said is we completed we wrote to the register file at the end of the clock cycle. So what we're going to do instead is we're going to write to the register file in the middle of the clock cycle, right, on the edge that is not the active edge, on the other edge. Okay, and by doing this, then what we can do is we can do the write back stage in the first half of the clock cycle, and then do the instruction decode in the second half of the clock cycle, and we can write the register that's written during the write back stage will be written in the middle of the clock cycle. Okay, so if we do this, then rather than stall cycles, we can stall for only 3 steps. We can stall for only 2 steps. Okay, and that way we can overlap the write back stage and the instruction decode stage where we read the register, and we can write in the first half of the clock cycle, so in the first 100 picoseconds, and then we can read in the second 100 picoseconds. So this is one possible optimization that we can do in order for us to reduce the number of stalls, the number of cycles that we lose because of this data hazard. Okay, well, this is fine. This is a nice optimization, but still, you know, it's not enough. I'm still losing 2 cycles, and I'd rather not lose these 2 cycles. So what else can we do to make things even better? Well, another thing we can do is called forwarding or bypassing. So again, this allows values to be written during this optimization here. It allows values to be written during a cycle and read in the same cycle. So basically, the value gets written in the first half of the cycle, and then it gets read in the second half of the cycle. Okay. So another optimization that we can perform is called or bypassing. So forwarding and bypassing is based on the observation that even though the value of S0 is written to the register for the write back stage, we actually know the value of earlier. When do we know, after what stage do we know the value of S0? Right, so after the execute stage, the value of S0 is available. We know what the value of S0 is over here. Even though we haven't written it back to the register file, we know what it is. Okay? And then the other observation is that for subtract, even though we read S0 in the instruction decode stage, when do we actually need the value of S0? Right, also in the execute stage. So the value of S0 is available after the execute stage of the add instruction, and the value of S0 is not needed until before the execute stage of the subtract instruction. So what can we do? What we can do is, rather than waiting for S0 to be written to the register file and then reading it from the register file, we can actually sneak S0 from the output of the ALU back to the input of the ALU for the next instruction to use. Okay, and this requires extra connections to our data path. And later on, you know, we will look at how we can modify, how we can pipeline the data path and apply this optimization to the data path. But for now, it's just important to realize that we can apply forwarding or bypassing to avoid having to stall in between these 2 instructions due to the data hazard. So this is a very common optimization that people apply to deal with data hazards, and that is to just apply forwarding to the data. Okay. Any questions about this?
Yes. Does that mean we connect the result of the ALU backward? No, there's only one hardware, right?
Yes, so we're going to have to take the output of the ALU and bring it back at the input, but you're going to need to have some registers to make sure that you don't you do this on the next cycle, not the current cycle, and things like that. So
Okay.
hold these kinds of questions until we look at how we're going to do this in the actual hardware. But for now, I just want you to abstractly understand that we can take the output of the ALU and bypass it back to the input for the next instruction. Okay?
Okay, thanks.
Yeah, you're welcome. Other questions? All right. So forwarding is a great way to avoid stalling, but it turns out that we cannot always avoid stalling by forwarding, because sometimes the results are just not available, and this is the case with a load instruction. So if I have a load instruction, okay, so if S0 is the result of a load, right, and then I have an instruction after that that's using S0, like a subtract instruction, okay, then I can't forward. Why? Because the value of S0 is not available after the ALU. When is the value of S0 available? If I'm doing a load instruction, when does the value of S0 become available? After what stage?
After the mem.
Right, after the mem stage. But when does the subtract instruction need the value of S0?
Before it.
Right, it needs it over here. Right, so I can't forward, right? Because here this is at 800 picoseconds. The S0 becomes available at 800 picoseconds. However, I need it at 600 picoseconds, right? So I cannot forward from the future. Okay, so it's not so in the case of a load instruction, it's even if we do bypassing or forwarding, it's not possible for us to avoid stalls. So in the case whenever we have a load use data hazard, what that means is we have a load instruction producing a value that's used later on. We call this a load use data hazard. Okay, then in this case, we have to stall for at least one cycle. So stalling is inevitable in this case. We stall for at least one cycle. And now when we stall for one cycle, now we can bypass the value from the mem stage to the execute stage. So here, S0 is available after the mem stage for the load instruction. So we take that and we bypass that to the execute stage. Okay? Is this clear? Any questions about this? All right, great. So the next hazard, before I talk about the next hazard, so we can actually, the compiler can actually apply some optimizations to avoid these kinds of stalls. So for example, one common optimization is instruction scheduling, which the compiler does, where it reorders the code to avoid having a load instruction immediately followed by a use of the value that was loaded. Okay, so for example, if I have this over here, I have these, in this code, I have a load instruction followed by an add instruction that uses the result of the load. And here I have another load instruction that produces a value that's used by an add instruction right after it. In this case, if I execute this code, I'm going to have a stall in between this load and this add instruction, and another stall between this load and this add instruction. So what I can do to avoid this is, as one of you was mentioning before, what we can do is we can take an independent instruction and move it in between the load and the add. Okay, so what we can do is we can take this load maybe and move it backwards. So here, if I want to execute this code, it takes 13 cycles, right? I have 7 instructions and then 4 stages, which are the tail. So that's 7 plus 4, that's 11. But I also have 2 stalls, so that's 13. However, if the compiler optimizes this code, it takes this load instruction, it moves it back over here. So now there are 2 instructions. There's an instruction in between this load and this add. So rather than stalling, I don't have the load use data hazard is no longer there. Okay, because the instruction that's using the result of the load is not right after the instruction that is producing that value. It's not right after the load. Okay, so here in this case, I don't have any stalls, and in this case, I will take 11 cycles. I have 7 instructions, so that's 7 cycles for the instructions, plus 4 more cycles for the remaining stages of the last instruction. Okay, so instruction scheduling is a powerful optimization for avoiding stalls whenever we have a load use data hazard. All right, any questions about this? Okay, so the next hazard we're going to talk about is a structure hazard. So again, a structure hazard is when the hardware structure, the same hardware structure is required by different instructions. So an instruction cannot execute because there's another instruction using a hardware structure that it needs. Okay, and it turns out that in the MIPS pipeline, we do not have structure hazards. And the reason we do not have structure hazards is because we don't use the same resource for 2 different stages. The MIPS pipeline doesn't use the same resource for 2 different stages. And in particular, we use separate instruction and data memories. So the instruction fetch stage and the memory stage are using different memories, so we don't have a structure hazard there. Okay, so there's no structure hazard between instruction fetch and mem stage. If we use the same memory for the instruction and the data memories, then we would have a structure hazard, and I'll show you an example of that. Another thing that the MIPS pipeline does to avoid structure hazards is that we can read and write to the register file on the same cycle. You know, this is something that I've been repeating frequently, and now you'll come to appreciate why this is so important. Being able to read and write to this register file on the same cycle allows us to not have a structure hazard on the register file. Otherwise, if we were not able to read and write from the register file in the same cycle, then we would have structure hazard between the instruction decode stage where we read and the write back stage where we write to the register file. Because we're not able to do both, we're able to do one or the other. And again, I'll show you an example of this. Okay, so let me jump over to the example. What I mean. So hypothetically, if the MIPS pipeline used a single memory for instructions and data, it doesn't, right? It uses 2 different structures for the instructions and data. But if it did use the same memory for instructions and data, we would have hazards between the instruction fetch and the memory stage. And let me show you how. Let's say I had a load instruction. Load instruction does instruction fetch, instruction decode, execute, memory, write back. Okay. And then I have a bunch of instructions that come after that. Okay, so I have this instruction add, then this subtract instruction, and this add instruction. So here, if I was using the same memory to fetch both data and instructions, then I would have a structure hazard between the memory stage of the load instruction and the instruction fetch stage of the add instruction. Okay, because when I come to do instruction fetch for the add instruction, I realize, oh, the load instruction is using the memory to load the data, so I can't use the memory to fetch the instruction. So what I would need to do is I would need to stall. Okay, I would need to stall so that the load here is using the memory to fetch the instruction. And then on the next cycle, here the memory is not being used because the add instruction doesn't use the memory. So here I can then use the memory to do the instruction fetch. Okay, so this is what would happen if the MIPS pipeline were to use the same memory structure to do both the instruction fetch and the instruction fetch and the data access. But since the MIPS pipeline uses different memories for that, we don't have this kind of structure hazard in the MIPS pipeline. Okay. The other example that I gave was for the register file. So the MIPS pipeline allows you to read and write to the register file on the cycle. However, hypothetically, if it did not allow you to do that, then we would have a structure hazard between the ID and the write back stage. So for example, over here, if I have a subtract instruction that writes back here on the 5th cycle, then when I come to execute the later instruction, this add instruction over here is supposed to execute instruction decode, so it's supposed to read from the register file on the 5th cycle. However, if I was not able to read and write from the register file on the same cycle, then this subtract instruction will be writing to the register file on this cycle. So the add instruction will not be able to do instruction decode here. So what I would have needed, what I would need to do if I cannot read and write on the same cycle, is I would need to stall, because I can't do both write and read on the same cycle. I would stall so that I don't do any instruction decode when I'm doing write back, and then I would do ID on the next cycle. Actually, I would still have a hazard over here because I'm writing back over here, so I still have a problem. I still have a hazard, and things can start getting pretty ugly in this case. Okay, but however, because we don't have this problem in the MIPS pipeline, because the MIPS pipeline does allow you to read and write to the register file on the same cycle. Okay, any questions? Okay, if there are no questions, then that is all for today. You can read more about what we covered today in section 4.5. And next time we will start talking about control hazards, and then we will look at how we can apply pipelining in the actual MIPS data path. Okay? All right, that is all for today, and I will see you next time. Bye, everyone.